Hello everyone and welcome back to Physical Geology 001A at West Valley College. I am Professor Farida Bakshi Musa and today we are embarking on a new chapter in our understanding of the planet, Geologic Structures. By the end of this lecture, you will have a thorough grasp of how rocks respond to stress, the ways they bend, break and fault, and how geologists observe and record these features in the field. So let's get started. When we look at the natural world, from towering mountains to deep canyons, what we are really observing are the results of immense forces acting over geologic time. By studying geologic structures, we gain insight into ancient forces, plate tectonic movement, earthquakes, mountain formation, metamorphism, and even where to look for Earth's resources. Every fracture, fold, and fault in the Earth's crust tells us a story. Some of the key structures that we focus on include bedding planes, foliation planes, dikes, sills, fractures, faults, and folds. As structural geologists, our goal is to observe these features, determine their orientation, and measure any displacement to better understand the Earth's dynamic past. So let's begin with concepts of stress and strain. Stress in geology refers to the force applied to a rock. Most commonly, these stresses originate from plate tectonic activity and the weight of overlying rocks. There are three main types of stress. Compressive stress, squeezing forces often found at convergent boundaries. Extensional or tensional stress, pulling apart, typical at divergent plate boundaries. And shear stress, side-by-side forces at transform boundaries. Now when stress is applied to rock, the rock's response is called strain or deformation. Each rock can respond differently based on its composition, temperature, and how quickly the stress is applied. There are three main ways rocks deform. Elastic deformation. The rock bends like a rubber band and returns to its original shape when the stress is removed. Plastic deformation. The rock changes shape permanently. Brittle failure. The rock breaks or fractures when exposed to stress beyond its limits. Temperature and moisture play a big role here. Warmer, wetter rocks tend to deform plastically, while colder, drier rocks are brittle. Also, rocks exposed to rapid, high-impact stress, such as from an earthquake, are more likely to fracture than to fold. Outcomes of these processes include simple fracturing, tilting and folding, stretching and faulting, each leaving distinct marks in the geologic record. Near the surface, most rocks are cooler and more brittle, so they tend to break rather than bend when under stress. When this break occurs with no significant displacement, it's called a fracture or joint. You will see joints forming as rocks expand after the removal of overlying material or when volcanic rocks contract as they cool. Joints are typically associated with tension rather than compression, but can also appear in parts of folded rocks that are under tension. Finally, compressive stresses can cause joint sets forming at angles to the direction of compression. Now let's talk about folds, which are visible evidences of rocks bending under compressive stress, especially in warmer and more ductile conditions. Folds in rocks can vary in size from microscopic to massive arching mountains. The basic terms: an anticline is an upward fold, while a syncline is a downward fold. If we aren't sure about overturning, we use the more general terms antiform and synform. The plane passing through the crest of a fold, for example this is the crest, is the axial plane. The sides are the limbs. A fold is symmetrical if both the limbs dip at similar angles. So this angle, if it's this way, the angle is the same, so it's a symmetrical fold. And asymmetrical if not. If one limb is tilted past vertical, the fold is called overturned. So an overturned fold would look like this, right? If both limbs are nearly horizontal, it's a recumbent fold. So this is your recumbent fold. Isoclinal folds are very tight with parallel limbs. Folds can be nested within larger folds, and erosion often shapes the landscape differently than the pattern of the folds themselves, depending on the resistance of rock types to weathering. When rocks are too brittle to fold, they break, and we see movement along these breaks. These are faults. How do faults form? Through different stress regimes. In compressive settings, you get reverse faults, where the hanging wall moves up relative to the footwall. In extensional regimes, you see normal faults where the hanging wall moves down. Thrust faults are a special kind of reverse fault with a low angle fault plane. These play a huge role in forming mountain belts, where massive slabs of rock can be pushed tens of kilometers. Strike slip faults occur where rocks slide past each other horizontally. Think of San Andreas Fault. In regions of extension, down-dropped blocks are known as grabens. Adjacent blocks are called horsts. So it's very similar to. So this is your graben. This is your horse. And this. These are classic features in places like the Basin and Range region of the western US. Some faults like the San Andreas or the Tintina Fault can show hundreds of kilometers of movement over geologic time. So how do geologists measure all these features in the field? We use two main descriptors. Strike, the compass direction of a horizontal line on the surface of a rock layer. Dip, the angle and direction in which the rock slopes down from that strike. Imagine a vertical wall. The strike is the compass direction of the wall. The dip is how much it leans away from the vertical. With a special compass clinometer, we record these orientations not just for bedding planes but also for fractures, faults, dikes and foliation planes in metamorphic rocks. When plotting on a map, we use specific symbols to include strike and dip, limb orientation, fold axis and more. So strike and dip is this symbol. It's a vertical and a horizontal horizontal line and a vertical perpendicular line. That's just strike and dip symbol. This mapping helps us reconstruct the structural history of a region and provides essential data for everything from resource exploration to engineering and hazard assessment. So let's quickly recap and summarize. Geologic structures reveal the forces and processes that have shaped and continue to shape our planet. Today we've covered the types of stress rocks experience, compressive, tensional and shear, how rocks respond through elastic or plastic deformation or by fracturing, classification and formation of folds, anticlines, synclines, isoclinal, overturn and recumbent forms, the conditions under which rocks fracture and the distinct types of faults, normal, reverse, thrust and strike slip. How to measure and map strike and dip, which are crucial for fieldwork and understanding Earth's history. As you continue your journey in geology, remember that every fracture, every fold, every tilted layer in a road cut or mountain cliff is a testament of Earth's ongoing dynamism. Thank you for joining in, and please submit read your study questions, go through the chapter in your textbook, come for my office hours, answer the questions. You're doing great, and if you have any questions, email me, message me. I'll see you in the next one.